Hi, everybody. I wanted to just do sort of an overview review of standard deviation so that you can recall it without having to watch all the lectures that are available to you. So we all know that when we use the word standard, we're talking about like a standard tool, like a ruler or something that we can conclude as a way of understanding the data better. It's a standard for communication. And deviation is just how far apart each score is from the measure of central tendency. So we can have those two terms. So deviation, a standard, is just a way to use common language to describe data. And we know that a deviation, just like deviant behavior, it's far away. It just tells you how far scores are from the measure of central tendency, which in the work we're doing is always going to be the mean. All right, this assumes a normal distribution is the most beneficial. So imagine then the scenario like this. I ask each of you to rate the level of attention that you can pay to Zoom recordings, and I get data from 5 students, person 1, person 2, person 3, person 4, and person 5. And so here are the scores. Scores always X, the way we're going to do things. Let's say the first person can't concentrate well, they say 2. Second person has no trouble, they say 8. Next person 5, then we have a 6, then we have a 4. So the first thing we have to do to make sense of these data is we calculate the mean. And of course, we do that by, I'm just going to shrink this a second here. Of course, we calculate the mean is the sum. You'll remember the uppercase sigma meaning sum of each score minus, divided by n. And in this case, the sum of all these scores, 2, 8, 5, 6, and 4, 10, 25 divided by 5 equals 5. So now we know the mean is 5. So 1, we calculate the mean. Secondly, we calculate deviations, which is just x minus m. We usually break this out. You probably maybe did this all at once in your last class if you didn't take 213. We're going to tease this out and do it in 2 steps, at least at this juncture. So we just take each score divided by n. 2 minus 5 is -3. 8 minus 5 is 3. 5 minus 5 is 0. 6 minus 5 is 1. 4 minus 5 is -1. Now, we know that conceptually, let's write this down over here. This I'll just maybe grab a different color here. Just make a note. We know that conceptually, the standard deviation is akin to the average deviation. And so you might think to yourself, well, here are all the deviations. Those are all the deviations. Why can't we just add those up and take the average? And that's because the very nature of these deviations necessitates that they will always sum to the same number. -1 plus 1 is 0. -3 plus 3 is 0. The deviations always sum to 0. And so if we calculate the average of that, we're just going to get 0. It's non-informative. And so what we do is that little kind of manipulation to solve this problem. We square the deviations before we sum them. So we square them. And you'll see this trick used later when we adapt non-normal distributions. So let's put the deviations squared. And so we get -3 squared is 9, 3 squared is 9, 0 squared is 0, 1 squared is 1, and -1 squared is 1. And so now we've gotten rid of all those negative signs. So now we can calculate the sum of squares. I'll just write SS. The sum of squares is just the sum of all the deviations, x minus m squared. And in this case, we just add 9 plus 9 plus 1 plus 1, 20. Next, we calculate the variance. I'll just write that formula here. Is x minus m squared, the sum of all those, the sum of all the x minus m squared. We calculate the variance, which is just s divided by n. From your last stats class or from working t-tests, you may say, hey, what about n minus 1? Isn't that how we calculate the variance? And the answer is no. That's how we calculate the variance when we're trying to extrapolate to a population. In this instance, we're not. We're just trying to find out the standard deviation of this very data set. We're not doing any estimating, so we just divide by n. So the variance is just s divided by n. The sum of squares is 20. There are 5 in the sample, and so we get 4 for the variance. And lastly, we take the square root of the variance to get the standard deviation. We'll squeeze this in here. Square root, I'm just going to use the abbreviation we use in Excel. The square root of the variance equals the standard deviation. And in this case, the square root of 4 equals 2. So that's the basics of calculating. What that means is then if we were going to interpret it, we would say the mean of this distribution, let's draw it out here, assume it's normally distributed. The mean equals 5. And each standard deviation is 2 units, so 5, 6, 7. So on average, scores are deviating from the mean by about 2 units. And so this is a little hard to see, so tiny, but that's how that would be interpreted. You did also see some new symbols. We talked about samples and populations. All of what we just did here was calculating standard deviation for a sample. And because it's an exact sample with known raw data, we use SD, writing it out in just regular normal language to represent standard deviation. Now, and the same M to represent the mean. If we were, however, using a really large, well-known set of data, a good example is IQ scores. We have gathered IQ scores from millions of people. Over many years. And we find out that the mean is approximately 100. And the standard deviation is approximately 15. And that's over all of these data sets. Now, it comes from so many data sources that we can't possibly go back and get the raw data. And so in this case, it represents the population. That is all the known data about the phenomenon. And the population would be represented using mu to represent mean, and lowercase sigma to represent standard deviation. And so if we were going to draw the distribution of IQ scores, we would have the normal distribution. That's what it would look like. And instead of writing m equals 5, we would, well, I'll put 100 because we're talking about IQ scores now. Mu mean equals 100. So we'll put the 100. And the standard deviation would be sigma equal to 15. So 115. And of course, sigma is 15. And so we could continue to draw these. Now we'll get into more detail with this later. In fact, I hope I'm not premature in introducing these terms, but you will have seen these before. And so that's just representing that sigma equals 15 in this distribution. So we'll be doing a lot of these solutions within Excel. You should watch the separate videos. Well, actually, I'll just pull up a spreadsheet here and do a quick little demo for you in Excel. No, I'm not going to actually. There are separate demos for how to do this in Excel, so I'll leave it at that so this lecture doesn't get too long. All right, thanks for tuning in. I hope this was helpful as a reminder overview.